Alright, so number 3, we just say x has to be at least 1. X is the number of non-word errors, at least 1, so x greater than or equal to 1. Or you could say strictly greater than 0. These would be the same thing since it's discrete. There is nothing in between them. And then what is the probability? Just be 0.9. You just add up all these, or everything but that. Describe that in words. That'd be no more than 2 non-word errors, or you could say less than or equal to 2. You could do that. What's the probability of that? Less than or equal to 2 is these 3, which is 0.6. What's the probability that x is less than 2? Well, then I don't include that. So it'd just be 0.1 and 0.2. So that's why it's that. Number 11 was the same thing, but I'm finding the mean. So finding the mean, you just multiply down 0 times that, 1, 2, 3 times that, times that, times that, and you add across all those, and that was 2.1. And then interpret it. You could just say, on average, these whatever make whatever x this much. So on average, undergraduates make this many errors in an essay. Now to calculate and interpret the standard deviation, we might need the formula sheet. So on the formula sheet, we have discrete random variables here right in the middle. And the mean is, this is just the add every x times its probability. This is the multiply down, add across thing. But then the standard deviation, that's where you take every single number minus the mean squared. And normally you divide by something, but here we're going to times it by the probability of that particular number. All both of these are really, is just like a weighted average in like a weighted standard deviation. So I went ahead and wrote out the formula. So it's just the first number minus the mean, which was right here, squared, and then times the, you can't see it, times the probability, then the second number minus the mean, and so on. And so that's 1.53, and how do you interpret that? Typically varies by, right, will typically differ from the mean by this number. Okay. This one, probability distribution, is simply where you take every value, and this one was a little tricky because it says x is the amount you gain. So you either gain 0 or you gain 3. Now both of these, the amount like you come home with is like -1 and 2 then. But you should be able to see that the average, then if you multiply down and add across, you just get 75 cents. So that would mean for every dollar you play, you roughly gain 75 cents. Well, that's a loss, but anyway. And then the next bunch of problems do with this Benford's law thing. It has nothing to do with stats. This is just a good problem to do stats on. There's no Benford's law of stats. Okay, so it's all about, well, you read it, so I just want to go over it real quick. Part A, I didn't put the answer. To show that something's a legitimate probability model, hopefully remember, we simply say all of these probabilities are less than 1, and they all sum to 1. Ta-da. And you could verify that by adding them up. Make a histogram. So here's the histogram, and we'd say it's skewed right. It looks to be centered around, I don't know, 4-ish, etc., etc. Mostly skewed right, most important thing there. Describe this in words. This is the probability that the first digit, actually not the probability, just simply the first digit is a 6 or higher, or at least a 6. What is the probability? 0.22. That's just take this plus this plus this plus this. Express at most 5. Okay, a little bit tricky. That means less than or equal to 5. Could be 5. 5 is at most 5. Okay, and that actually you could just do 1 minus this probability because these are complements, or you could add up all of these. Okay, so now same problem, but now we do what outcomes make up A. A is the first digit of 7 is greater. Oh, okay, so that could be a 7, an 8, or a 9. Okay. What's the probability of that? You just add the 3. Okay. What outcomes make up B? B is odd, so 1, 3, 5, 7, 9. Just add them all up because they're all mutually exclusive. You could just add them. C, what outcomes make up A or B? That would be all the odds plus 8, essentially. What's the probability of that? Well, it would be 1 plus 3 plus 5 plus 7 plus 8 plus 9, all those columns, but that's not the same. Why is this not the same as this? because A and B, 7, 8, and 9 are all mutually exclusive. They can't happen. You can't get a 7 and an 8. But you can get a number 7, 8, 9 that's also odd, sure. So we have an overlap of 8. So the 2 should be off by whatever the probability of 8 is. So this number, and if I add those, I don't know, these two numbers should be off by whatever the probability of 8 is. Okay, more Benford's law. Someone's trying to be sneaky, and Benford's law is going to catch them with math. And so, well, first we're saying here's what would happen. This picture here is what would happen if the probability was the same and you just randomly picked. So why should the mean be right here? Well, because this is symmetric and uniform, so the mean's going to be right in the center. So now if you actually follow Benford's law, what's the expected value? That's just asking what's the expected value of exercise 5. So this is the answer, but this just comes from multiply down, add across, and here's its interpretation. And then the standard deviation, number 17, I'll come back to the other one. 17, calculate the standard deviation of the first digits. So 17, this 2.41618, that's simply take every number minus the mean, square it, multiply by its probability, add them all up, square root at the end. I mean, I say simply, that's a lot of work, but this problem had, maybe a few too many data points. Okay, back to this. So it should be 3.441, but what's the what is y greater than 6? Y greater than 6, that's up here. This is y. And so you're just supposed to say, what's y greater than 6? So that'd be this plus this plus this. Well, each of these is 0.1. So it'd just be 0.3. So 0.3, or 0.33333, because there's not, sorry, not each of those is not 0.1, because there's only 9. So, but anyway, under Benford's law, it should be 0.155. That's just looking at the chart back in number 5. And then, so compare them. Well, if you're looking at a suspect report, I didn't actually talk about B either. For both of them, if you're looking at a suspect report, you could say, oh, well, is the mean closer to this or this? Or, yeah. Okay. 17, the standard deviation of y is, you still do the same thing. It's just every data point, 1 minus the mean, which was what? 5. 2 minus 5. 2 minus, okay, and then the probability of each is 1/9. And so that's where that number something came from. Sorry, totally lost my train of thought. That's where this 2.58 came from. And here it says this would not be very good because the standard deviations actually are pretty similar to each other, so it'd be hard to tell. Okay, 21 is supposed to be pretty simple, but I get it's a little tricky looking. But it's simply if you're picking a random number between 0 and 1. So if I were to graph a distribution, if it's random, all of these should be the same, and it's like a continuous variable because there's an infinite number of numbers here. So what's the probability greater? Oh, so this would just be, I have to just shade the graph. I can't make a probability distribution table. And so what's the area there? Well, that would just be 0.51. And then the key is that this other one, even if you include that, is still 0.51 because the probability of getting exactly 0.49 in a continuous variable is essentially 0. And then this one, this is 18 wide, 0.18. This is 16 wide because if you go all the way out to 1.27, nothing happens out here. So really you just go to 1 and then it's 16. So then this, you just add them because those are mutually exclusive, so the OR can just be added. So 0.34. Next was just a chapter 2 question, really. Find the probability y is less than 6, where y is a random student. Well, this is just a student, so chapter 2, just draw a normal curve. And this said follow the 4-step process, but we don't really have to for these. And so basically we just get the normal curve, shade to the left of 6. You have to define it somewhere for full credit, right? So here's normal, okay? And then it's just normal CDF to finish the problem, really. And so they went ahead and found the z-score and then found normal CDF, so about 7% chance. But we could have just done normal CDF right away. I'm not going to review how to do that. If you need help with that, I can go back and look at it. This one also pretty similar. Do they draw a picture? No. I'll draw a picture for this one. So that's all it's asking for is what's the area between 0.52 and 0.6. This is for part A. And so normal CDF, yada yada, and they got this using table A instead of normal CDF. What if in fact 72% said it? Well then, what's the probability? Oh, so it'd be the same picture, but I'd be shading above 0.72, which is way up here, and is basically 0. And then we would say, since that p-value is basically 0, we would reject. And that's all it's asking, right? This probability is so small, it's good evidence that some people don't. And that is the whole idea of later chapters, but this was earlier, before we formally learned all that. And then, real quick, the multiple choice, maybe real quick. So if you have 2-car garages, what percent of households have more cars than the garage can hold? So this is just saying the probability of, do they give it a variable? Yes, x is more than 2. Oh, so that'd be this plus this plus this, which is b. What's the expected number of cars? That's multiply down and then add across. So C, essentially. Scroll down. So C, a deck of cards contains 52 cards. Yep, that's true. Okay. If you make this wager, what will be the amount that you win? This is simply your expected value. So we should just make a quick little probability distribution. And so you either make $10 or you lose 1. That's 4 52s, that's 48 52s. Then you multiply down and add across, you get negative 8 52s, which is C, negative 15 cents. And then lastly, this one, which would you prefer? Just draw it out. So we either make $2 if we get a heart, there's 13 hearts. There's also 4 suits. You could just say a quarter of the time we'll get $2 and 3/4 of the time we'll lose $1. And so our expected value is negative a quarter. And so we would want wager 1 because negative 15 cents is higher than negative a quarter.